Okay, well, welcome everybody to the last meeting in Peyton Hall of the academic season. And it's great to be here. You know, the night's agenda is going to be an interesting one. We've got a few things that we want to take care of right up top. And we're going to have an election of officers. The bylaws actually allow us to incorporate as a 501(c) or whatever. Nonprofit. We are a corporation, incorporated, I guess I should say, a nonprofit. And so we have bylaws and we elect officers once a year. And so we'll talk about that in a moment. Is Dan here? Dan Updike? Dan? Oh, good timing. Is that an entrance? All right. In a moment, Dan will help us. Dan is the nominations chair this year. Thank you, Dan. Just to talk about the agenda real quick here, I want to tell you about an interesting summer project that has cropped up with the Unistellar Telescope. Very interesting piece of equipment that we've come into possession. Just talk a few minutes about that, and then I'm going to turn it over to Victor. He'll introduce our guest speaker tonight, and we'll talk about some very heavy topics. And we'll take a quick break after that. That'll go about an hour, and we will then come back. And Maya Chu, a AAAP member, is going to give an Unjournal Club on some studies she's done on variable stars. They are our Lyra variety. And I'm going to share the exciting finding that was in the press just a couple of weeks ago, and that I wrote up in Sidereal Times a little bit about the possibility of a biosignature signal coming in from JWST observations of an exoplanet. Very exciting stuff, but is it real is the question. Then we will go into some other activities going on in the club. And just to mention, Ira will talk about the survey for the field trip we've been discussing to Air and Space Museum in DC, and we'll talk about outreach and observatory events. And if I could advance my slide, I would, but I cannot advance my slide. It's a Windows thing. Now that Windows 10 is antiquated, it's like you can't really do what you want to do. Maybe it is definitely a Windows thing. Bear with me, guys. Sorry about this. Okay, so come back and share. I am going to do that. A little clumsy here. Sharing the screen. So here's the situation. I would like to ask Nominations Chair Dan Updike, AAAP member, and helped us with just putting our ducks in a row for the nominations to conduct the election. So you see on the screen before you who the candidates are, and no big surprises here except Ira stepping up into the position for treasurer. So we do need to do a formal, semi-formal count, and we need to establish that we have a quorum. Dan, would you mind just like saying those fateful words? Sorry, did I say fatal? Oh, you got that.
No, that's the mic there.
That's the mic. You got the mic. It's also a baton. Yeah. We can just ad-lib it.
All right.
Ad-lib it or.
All right. First, I'd like to thank everybody who responded to our call for nominations. I heard from one member of the general membership who asked about the responsibilities, but they didn't follow up. At this time, we have one candidate for each board position. All are either continuing in their current roles or have confirmed their willingness to serve. Obviously, the slate of the candidates there. Before proceeding, is anybody, any nominations from the floor?
Don't be shy.
No? Okay. Since all the positions are contested, proceed with a voice vote on the full slate. All those in favor?
Aye.
Keep your hands up.
Yeah, we need to do a count.
Put it in here. And
Jean,
read it, okay?
Secretary Jean will record the findings.
We have 3 raised hands in the
2,
4.
2, 3, 4, 5, 6.
Oh, I was getting 34. Did I jump?
7, 8, 9. 1, 2, 3, 4, 5, 7,
1, 2,
8,
3,
9,
we got 5 in, it looks like 5 in here.
11.
Oh, 6, 7, Larry.
I got 27, yeah, 27,
In the
28
room?
in the room.
Okay, it looks like there's, 6 or 7, probably 7. I think I counted 7.
Okay, and we've established the quorum is 32, 15% of 211. We're good.
Yeah, good.
We're good. So with that, Dan, you pulled it off.
All right,
Okay.
congratulations.
You appreciate that. Yeah, I just want to give a quick thanks to my fellow board members. And you guys have been tireless, and really your energy helps run this organization, makes it work. Couldn't say enough good things, so I won't take the club's time, but you know how appreciated you are. So let's have another year at it. Keep astronomy alive in our area. We all know more than ever, science ed is a top of the list of needfulness right now. And also, last time I'm going to say it, thank you, Michael Matrano, for your 18 years as treasurer. You kept us solvent in more than one way, so thank you. And welcome, Ira. A couple of months ago, the club acquired a very generous donation of a Unistellar EV-Scope 2, one of the latest generation of smart telescopes. Many of you have gotten involved with smart telescopes, particularly the ZWO C-stars, and they are taking the field by storm. As much of a revolution as we had several years ago with CMOS sensors coming into play, now the smart telescope is playing a major role in our ability to reach other people to do astronomy. EV-Scope Unistellar is particularly well suited. It's a lot like the C-star that you're familiar with, but it has some novel features that we don't need to get into right now. But when we recognized that we had this wonderful telescope on our hands, and yet all of us were pretty preoccupied with our own telescopes and the club's observatory scopes and so forth, we discussed this, and I made a proposal. Victor and I talked about this. I think I ran it by you a month or two ago, but the short story is that it seemed an ideal telescope to try to reach out to our younger members, our student members of AAAP, and to engage them in becoming masters of this telescope, learn the software, how to use it, and then actually use the scope to do observations and learn the night sky. Maybe for many young members, the first opportunity to actually image Messier objects on their own. To do that this summer as a summer project, to take the scope with them into their own hands, to share it amongst their fellows on the team, and then to come back next fall and give a little maybe 10, 15-minute talk to the club, to all of you, and see what they've learned. And so to my great joy, when I sent out a note proposing this, I ended up getting 16 student members with a positive response wanted to participate in this. And that's an excellent thing. It's outstanding. So I've asked them to self-organize, and they're going to impress us with their ability to do that. We've had an orientation session out at Washington Crossing Observatory just a couple of weeks ago, and it's a great telescope, I tell you. I almost want to get another one because this is an amazing piece of equipment. So enough said about that. It's unique in its characteristics like the C-star, but this is a 4.5-inch Newtonian, and the sensor is replacing where the diagonal would be on a Newtonian. So it's a unique setup and extremely well designed. The software is very clever. So enough said about that. I'm really happy that a donor who right now we're saying is anonymous, but we got to thank him again, as you said at dinner tonight, because that was an outstanding donation to the club. We do have a staple of a lot of scopes. So in passing, let me just say, if any of you are telescope-less and you want to take one and use it at your home this summer, you know, we have other telescopes in the stable that club loans out for free to members. Some really nice pieces of equipment, and some of them are actually out at the observatory. You can see them there. So yeah, this is basically what I just said, and now my PowerPoint is advancing. So just when I don't need it. This is an example of some of the very first images grabbed by the students a week ago Friday, and these are literally a few minutes of exposure with this smart telescope. So it's a cool thing, and we look forward to many more nights with it. I will say it's interesting what's up in the sky right now. There's a lot of galaxies, and they happen to lie right on the meridian. Won't happen too much longer. So if you're interested in galaxy observing, now's probably as good as it's going to get as these guys begin to recede into the west. This is our night sky right now, and each of those blue symbols is a galaxy of magnitude 11 or brighter. A lot to take in and a lot of potential targets. So with that, I think I'm going to ask Victor to come up here and take over the meeting and introduce our speaker, and maybe there's a good time to swap computers as well.
All right, well, let me, while we're setting up here, give you a quick introduction. Our guest speaker for tonight is Professor James Stone of Princeton University. He's going to talk about black hole accretion. Accreting black holes power the most luminous objects in the universe, including active galactic nuclei, quasars, and gamma ray bursts. Recent advances in computational methods allow calculations of the structure and dynamics of such flows from first principles. Moreover, observations from the Event Horizon Telescope and the James Webb Space Telescope are providing new insights into black hole accretion in a wide range of environments and on scales down to the event horizon. Professor Stone will summarize some of the recent progress that has been made in trying to understand the remarkable plasma dynamics of accreting black holes. A few words about our guest speaker. Professor Stone's research program centers on the use of large-scale direct numerical simulations to study the gas dynamics of a wide range of astrophysical systems, from protostars to clusters of galaxies. Almost all of this work requires development of advanced numerical algorithms for astrophysical gas dynamics on modern parallel computer systems. This says math to me. Makes me
Nervous.
Makes me very
Makes me nervous too.
Yes. Professor Stone is one of the primary developers of the Zeus code for astrophysical MHD, magnetohydrodynamics.
Just waiting to join.
And more recently, he and his collaborators have developed Athena, a high-order Goodenough scheme for astrophysical MHD that uses adaptive mesh refinement.
Well, thank you. Thank you for the invitation again to speak. I think the last time I presented here was 2016, almost 10 years ago. So it's a pleasure to be back. And I thought I would tell you about some of the research that's going on here in Princeton on the topic of black hole accretion. And I feel like this is actually a cutting edge area of research. Of course, it's very subjective. And so yeah, I'm trying not to make this too technical, but if you have questions or if I'm not explaining things well, please interrupt me, please ask questions. I'm happy to answer and discuss this more if you like. So, and I'll try to keep this just 45 minutes, I think, or 40 minutes. So why would we care about black hole accretion? And the reason is because accretion powers all the most luminous objects we know in the universe. Gram for gram, accretion onto a black hole is far more powerful than nuclear fusion, which, as you know, powers the stars. And so accreting black holes, sort of gram for gram, are much more luminous than are the brightest stars. And so quasars, X-ray binaries, so-called ULXs, ultra-luminous X-ray sources, just by their name, you know they're very bright. All these sources are all powered by accretion on the black holes. And moreover, black hole accretion plays a very important role in other ways. It determines the growth of black holes over the course of the history of the universe. And feedback from accretion onto active galaxies is turning out to be very, very important for galaxy formation for very large scales. And so we need to understand this to understand these problems. Now I've lost my, here we go. So the idea that black holes were affecting their environments or that they even existed has been around for a very long time. In fact, I think the first evidence for, indirect evidence for a black hole goes back to optical images of M87, this deep image taken by Curtis in 1919, where he noted in the research paper a curious straight ray emanating from the center of the galaxy. You can see it off to the right. It's a relativistic beam of plasma that's emitting optical photons and is seen as this jet, this straight ray. And then once radio telescopes were built, the first radio telescopes just after World War II in 1947, they quickly discovered these very powerful radio sources in the sky. And with modern instruments like the VLA, we now resolve the relativistic jet inside M87 to this beautiful beam of plasma coming out from the center. The dot in the middle here is where the black hole is located, the center of the galaxy is located. So clearly these black holes are doing something, or something interesting going on at the center of these galaxies. And we thought it was related to black holes, and somehow black holes produce these relativistic jets. But really, sort of the proof of the pudding has come from this Event Horizon Telescope, which I'm sure many of you have heard about. I hope you've heard about. Was certainly in the news a lot over the last few years. So by going to shorter wavelengths, so this telescope operates in the sub-millimeter range, and by going to longer baselines, and this telescope is a collection of telescopes around the world, literally around the world, from the South Pole up to Greenland and from Hawaii to Chile. Each of these telescopes is observing the same source at the same time. Their signals are combined together to give you the effective resolution of the entire diameter of the Earth. It's the largest you can possibly make a telescope on the Earth. And using shorter wavelengths, you get the highest resolution possible. This, wavelength divided by diameter is your resulting power. And so this is the biggest diameter you're ever going to get on the Earth, and it's a shorter wavelength. And with this collection of telescopes, we've now made the first image, resolve the event horizon of the black hole at the center of M87. So what I wanted to show you with this, amazing image from the Event Horizon Telescope, which is basically showing you millimeter wave emission coming from relativistic electrons just outside the event horizon of M87 as they're falling in through the event horizon. So we're literally watching the plasma as it's accreting inwards into the supermassive black hole at the center of M87. This resolution of micro arc seconds is required to actually resolve this. And we now have time images. We're collecting images at different epochs and watching the motion of this. We're hoping to make a movie over the next 5 to 10 years of this accreting plasma as it's spiraling in to the black hole. So we now begin to collect images, direct images of what's going on in the event horizon of these black holes. And so it's making this accretion extremely of even greater interest to understand exactly what's going on. And in fact, to interpret these images, what we need, here we have this wonderful image of M87. We also have it of the black hole at the center of our own galaxy, Sagittarius A star. And there's been a huge amount of analysis to try to interpret, what does that ring mean? Like, what are you actually looking at? And in fact, there's been a big project to run thousands of general relativistic MHD simulations, GR-MHD calculations of the plasma dynamics around black holes. Each little postage stamp here is a different simulation run with a different parameter, different black hole spin, different magnetization, different orientation of the disk to your line of sight. And then those simulations are ray traced, general relativistic ray tracing. It's very important to take into the light bending effects of the general relativity in the near horizon region to make a proper image of what you're actually, what a telescope would actually see. So then they're ray traced back to the observer to make these synthetic images. In fact, this is a collection of movies. So each simulation has been run for many, many thousands of orbits of the plasma around the black hole. And then from all these images, we can make best fits to which particular set of parameters, which images from all these different calculations fit the observed rings that we see in M87 and Sagittarius star. And from that, we can interpret what the mass of the black hole is, what its spin is, and what the basic properties of the plasma accreting on the black hole are. And so we're able to actually extract quantitative information about the black hole that we're observing by comparing the dynamics of the accreting plasma with what we observed. And so this has been a huge effort in the community to calculate these images and to understand what's going on. So how do we do that? I mean, how do we make these synthetic simulations, if you like, of the plasma dynamics? Well, it turns out that it's not so difficult. The equations of motion for the plasma, which is electrons and protons, are a simple set of conservation laws: conservation of mass, conservation of momentum, conservation of energy. They're a set of coupled partial differential equations. And so we just have to solve those equations on a computer. Solving them by pen and paper on It's just not possible. There are, in general, no analytic solutions in full 3D and time-dependent flows. So you rely on computers to find specific solutions to these equations. And how does that work? Basically, you divide space up into individual grid cells, and you store the mass, momentum, and energy of the plasma in each grid cell, and then you update the conservation laws according to these equations of motion and evolve the density and velocity and pressure on the grid according to the conservation laws. We use these adaptive meshes as I will explain them. They're in regions where there's small scale features. You use very small grid cells which adapt to the flow. And in regions where there's not much happening, you use very large grid cells. And so, of course, there's a lot of applied mathematics that goes behind developing these algorithms for solving these equations of motion. But the general idea is pretty straightforward. Using these very, very large meshes, grids of solutions of plasma dynamics to calculate these models. And because these calculations can involve very, very large meshes with billions of grid cells, they're very expensive to run. They're very computationally expensive. They don't just run on your laptop computer. They need to run on the largest computers available. And today, that means so-called exascale. Exa meaning 10 to the 18. And so we have computers now capable of 10 to the 18 floating point operations per second. They can do 10 to the 18 adds, subtracts, or divides per second. Even for an astronomer, 10 to the 18 is a big number. These computers are incredibly fast. They are the largest computers in the world. They fill up an entire room. They're limited by how much power that you can generate and run a machine on inside a building. And there are two today currently in the US. One called Frontier is at Oak Ridge National Lab, both run by the DOE. One is at Oak Ridge. The other is Aurora at Argonne in Chicago. Both machines have roughly the same performance, about 1.5 exaflops each, about 1 billion times faster than the fastest computer we had available about 40 years ago. So the growth of computing power has been exponential over 40 years and is now resulting in exascale computers that we can now use. So these are the computers that we're using to run the calculations that I'm showing you later today, are all run on these machines. The challenge is that these computers are not easy to program. They don't just run normal languages like C++. They have their own programming environment, and each vendor, each manufacturer has its own programming environment. NVIDIA has their own environment called CUDA. Intel has their environment called SYCL. AMD has their own environment called HIP. They're all incompatible. You can't run one code on different architecture. So this is a big problem for application scientists because we can't write codes that work on every different machine. We just don't have the resources to try to do that. But fortunately, computational scientists, and especially computer scientists, are very smart. They've developed languages and libraries that allow you to get around all of this. And so nowadays, we are able to develop codes that work across all these machines. And the code we work with is something called Athena K. K standing for Cocos, which is a C++ library that allows you to run code on any architecture you want, not just these exascale machines. It runs on my iPhone, it runs on Androids, it runs on my laptop, it runs just everywhere, just using C++. And so it's a really wonderful tool that can be used to develop these application codes that we then can run on the world's biggest computers to do these calculations. And so what is Athena K? It's basically an adaptive mesh refinement framework code that implements various solvers for GRMHD and radiation transport and other physics that we need to study black hole accretion. It runs on anything, CPUs and GPUs, developed by a loose collaboration of scientists. I wanted to show this slide because developing the software is really a big part of what application scientists do nowadays. We can't just buy software off the shelf that solves the GRMHD equations of radiation hydro that runs on Frontier. We have to develop that ourselves. And so we spend a lot of time developing the numerical algorithms, the applied mathematics, as well as implementing these on big computers. And the numbers at the bottom just show you, you can run it on my laptop when it actually runs and doesn't crash. It runs at some measure of performance, some number 34. But then if I run it on a NVIDIA H100 GPU, it runs at 677, roughly 20 times faster. And so you can see the increase in performance that you get by switching from CPUs to GPUs that are much more powerful. And all the machines that I just showed you, these exascale machines, are all built out of GPUs. You have to be able to use GPUs nowadays, not because they're so powerful, but because they're very energy efficient. They provide the most flops, floating point operations, per watt of power. And since the limiting resource in building these machines is not money, it's electricity. And so you need to have the most energy efficient processor you can to build the largest machine available, and those are GPUs. And that's why GPUs are used. GPUs are a lot more expensive than CPUs, but they're still used in these big computers because they're so much more energy efficient. So how do we know these codes work? Like, how do you know that any of this is right, that what we're calculating has got anything to do with reality? So we have to validate these codes. We have to test them. We have to compare them against known solutions, known analytic solutions, of which there's very, very few available. And so the other alternative is to look at other numerical solutions. So a quick aside, the way we do that, how do we compare to other codes, is we validate it on things like standard fluid dynamical instabilities. And the very famous one is the Kelvin-Helmholtz instability. You're familiar with this from everyday life. This is when two fluids flow past each other with different velocities. There's an instability in the shear layer between them, and it causes these rolls to form. And you may have been lucky to see these kind of clouds that make these rolls on a windy day. That's Kelvin-Helmholtz instability between two layers in the atmosphere moving at different velocities. Or in Jupiter's great red spot, you can see these beautiful vortices that are being formed by K instabilities in the atmosphere due to shear in the winds of Jupiter's atmosphere. So it's a very well-known instability. It goes back to Kelvin, after all. It's been around for centuries, basically, Lord Kelvin. And so we can calculate the evolution of this instability. We can take two fluids, one moving to the right and then moving to the left on the top and bottom, and we can just give a slight little perturbation to the interface, and we can let it go and calculate using these codes what happened. You can begin to see the roll. It starts to roll up into this cat's eye, sort of looks like those clouds for a moment, and then it gets more and more nonlinear, and then suddenly secondary instabilities appear. There's rolls that appear on rolls because there are additional secondary instabilities appear. It turns into turbulence, and you see this complex fluid dynamical flow as these two fluids mix from the KH instability. And it's very complicated and beautiful to watch. And is it right? Is this actually correct? Well, we can actually validate this because we can take solutions calculated by different codes. So this can see that each row is a different time. You watched the movie, and so you saw it progress in time. And this column here is being calculated by a spectral code, a very accurate code that gives you a resolved solution. So we know that if we increase the resolution in this code, this answer doesn't change. So this is the answer to this flow. And this is the same answer computed by this Athena K code. And you can see pixel by pixel, it's exactly the same. That this Athena K is reproducing the converged solution generated by the spectral code. And we can be better. We can calculate the actual error by subtracting the two solutions and measuring the amplitude of the difference between the two solutions. And there's a 1 part per million difference integrated over the whole volume in those two solutions, which we consider to be good enough. So we know that we're reproducing this fluid flow correctly. And this gives us great confidence that our solutions for all the stuff, the rest of the stuff I show you, are correct. We have many, many other test problems that we then run against to make sure this is all working. So let's try running black hole accretion flows with this. So the right-hand panel is showing you the electric current density in the plasma in an accretion disk in this two-dimensional slice. This little square represents a slice. It's like taking this pie-shaped accretion disk and cutting out a slice of it and then looking at the edge of the slice. This is the evolution in time of what that plasma flow would look like. You can see the development of the structure, and that turns into turbulence because, again, another well-known instability, not the Kelvin-Helmholtz, but now something called the magnetorotational instability. Turns out these magnetized accretion flows are subject to another kind of fluid dynamic instability that we can study computationally, and it results in turbulence. And we use these calculations to study the nonlinear regime and the properties of this turbulence. And this turbulence is really important because it's what transports angular momentum in the flow. And angular momentum transport's necessary. For stuff to fall into the middle, angular momentum has to be transported outwards. Otherwise, it would just remain in circular motion around the black hole forever, like the Earth circles the sun. The only way you can get the Earth to fall into the sun is if you get rid of its angular momentum. And in the same way, the only way you can get a proton to spiral into a black hole is to get rid of its angular momentum and make it fall inwards. And so this instability is the mechanism by which angular momentum is lost and the plasma flows into the middle. So this is the image you get on a laptop or a regular computer, if you like. And then this is the image you get on an exascale computer, where you can run something which is thousands of times higher resolution. And you see these tiny, incredibly tiny structures that appear at these very, very high resolutions. In fact, so small that this projector, and even my laptop screen doesn't have enough pixels to show you every grid cell that was used in the calculation. So you have to zoom in, blow up a region to be able to see the individual grid cells that were used in the calculation and see this very, very small structure that emerges in this turbulence. And so go back to that M87 image. This is what's going on inside that image somewhere. This plasma is turbulent, generating these incredibly small scale structures and turbulence. And we're trying to understand the properties of that turbulence through these numerical calculations. And so exascale has just been incredibly enabling because we're able to run these calculations that we would never be able to run before up to now. And so this has been really a boon to this kind of science. Yes, please.
On continually with time, what happens? Does it go on forever?
It keeps going on as mass is accreted. Eventually, it'll accrete whatever supply of mass there was, and then it'll all shut down. So if I'll show you some calculations in a minute where you start with a donut of plasma. It just starts accreting inwards. Eventually, all that stuff will have accreted inwards. Some of it will flow out, and then it all sort of shuts down after that. Okay, so there's one other thing that exascale enables. It's not just running higher resolution so we can see even finer scale features. It's also enabling you to add more physics. And really important piece of physics that needs to be added is the radiation transport. There was the word math used in the introduction, and I tried to avoid equations, but there's one equation here, and I hope I can then explain it easily. But the basic idea is that, yes, matter is falling into this black hole, but photons are trying to get out. The matter is being heated up, it's releasing photons, and those photons are trying to get out, and they scatter off electrons and produce forces. They produce an outward force, a radiation pressure force, that's trying to prevent the matter from falling in. And when those two forces balance, that's the so-called Eddington luminosity. So if you just balance the inward force of gravity on the right-hand side, gmm over r squared, if you're far enough in the black hole, the Newtonian form for gravity is just fine. So you can use the gravitational force on the right-hand side, and that balances the radiation force, which depends on the luminosity L there. And so making those two things equal, you can solve the equations for the Eddington luminosity, the point at which these two things would balance. And so if the black hole is accreting material fast enough that the outward going radiation has the Eddington luminosity, then the outward force of radiation is balancing gravity. And something interesting is going to happen. Will it accrete? Will it not accrete? What will happen? It's confusing because if it stops accreting, it stops generating photons. Then it'll fall in. Falls in, makes photons. Then that's going to stop accretion. What's going to happen here? It's all very confusing. And so adding, however, radiation transport is very complicated. Radiation transport in general relativity for full transport methods is really, really complicated. And so it's taken exascale computers for us to be able to run these calculations without very grossly simplifying approximations. So only recently can we be able to run radiation GR MHD calculations to see what's going on. And so my group and I have been looking at this survey of black hole accretion with different Eddington ratios where we increase the mass accretion rate so it's above the Eddington luminosity and then decrease it so it's below the Eddington luminosity so we can see what happens over a range of luminosities. We have different black hole spins, different magnetic field topologies. You can see the arrows are showing you the shape of the magnetic field initially contained inside the torus of plasma. So we can study what different magnetic field geometries do. And this is, again, being very revealing. What happens? So here's the, this is the initial condition, this donut of plasma. It's a slice through this donut. And then at late times, it turns into this with radiation transport. It turns into this kind of very, very fat accretion flow. And the panel on the right is an equatorial slice. That's what the flow looks like in the middle. These are two-dimensional slices of the full three-dimensional volume. The one on the right is the equator, and the one on the right is a poloidal slice. And if you set it moving, you can see this MRI turbulence that I showed you before, but now in the global context of an accretion flow in which there's radiation pressure dominating. This is where the radiation field completely dominates the energy budget of the flow. And all the radiation fields escaping out the hole. So what you notice immediately is that black hole accretion flows have these vacuum funnels above and below where matter can't enter. Matter never gets into the region above and below the black hole, and that's where all the photons can escape. So even though you're accreting at luminosities greater than Eddington, the radiation can flow out the poles, and that's what enables accretion rates that exceed the Eddington value. It's not spherically symmetric. It's in this non-spherical geometry, and the radiation leaking out the poles is what's allowing these radiation-dominated accretion flows to get going. So again, there's a big effort to try to understand exactly the physics and dynamics of these radiation-dominated models. Okay, I'm gonna, there was lots of other results that I could talk about, but in the interest of time, I just want to move to one other, interesting question, namely, okay, we're learning a lot about black hole accretion flows and exactly how they work, but another outstanding question is how do you feed this matter in to begin with? Where is that gas that's accreting in M87 coming from? And how does it, if you have a super Eddington accretion flow generating all this radiation and so on, how does it affect the large scales? What does it do? Does it stop matter from falling in from very, very large scales? So these are also fundamental questions that are beginning to be addressed now, again, using these computational techniques. And let me just show you, for example, a motivation for this. If you look at composite images of clusters of galaxies like Perseus, if you look at the X-ray in the blue, optical in white, radio in red, well, in the X-ray, you see these dark holes. So the X-ray is coming from very, very hot plasma, which is trapped in the gravitational potential of the cluster. If there are dark regions, that means there's holes in that plasma. There's regions where there's no matter, none of this relativistic electrons. So there's a bubble, a very low density there. Where did that bubble come from? And those bubbles are actually connected to, if you can barely see in the very middle, there's very, very small little dark filaments. Those are optical filaments, very dense gas, which cooled down to only a few tens of thousands of degrees Kelvin instead of the millions of degrees that the X-ray emitting plasma is at. And so there's something going on at the center of this galaxy, which is generating these very large bubbles, which are propagating to very large scales and producing these very narrow filaments of cooler gas. And this is very, very curious. We think this is an example of AGN feedback, that there's a black hole at the center of the galaxy at the center of this cluster, and this black hole is emitting a jet, as we saw in M87, and outflows and radiation, and those things are affecting the galactic cluster and environments. And those are very, very important. That feedback is very, very important for the structure of the gas in very large scales. The challenge of this calculation, however, is a huge range of scales involved. You have to go from the whole galaxy scale, represented by the M87 image on the right, all the way down to the horizon, where M87, the ring that was averted by the EHT. And if you if you measure what range of scales that is, that's literally billions of orders of, or a billion factor of 10 to the 9 in scale, in radius. So you got to go from milliparsec scales, which is where the event horizon is, up to megaparsec scales. And you got to go from time scales, which involve days, which is the orbital time that the event horizon of the black hole, and you got to evolve for gigayears. That's how long the cluster evolves for. So how do you do a computation that can span this enormous range of length scales and enormous range of time scales? And the technique that's emerging is the so-called zoom techniques, where you start a calculation at the top there, which only has a narrow radial range. You evolve it for a while, and then you move the inner boundary in closer, and you evolve that region for a while, and you move it in closer until you make it all the way down to the event horizon. And then you're capturing the flow dynamics across the entire range. But because your time step is a day, you can't evolve it for billions of years. You can only evolve it for a few months or maybe a few years at scale. So then you zoom back out again, evolve the outer regions, and then zoom back in, and you zoom out, zoom in many, many times. So you can follow the flow all the way from the horizon to these larger scales. This is a new technique that a graduate student here at Princeton has been pioneering and doing a lot of really interesting calculations. And I just wanted to show you a movie of what results from one of his calculations, where you can now finally zoom in over these 6 or 7 orders of magnitude in scale, starting at the galactic scale. I'm not sure if you can see the scale here, but this is 30 kiloparsecs on the outer scale here. So this is the outer box of the calculation. This is the X-ray emitting plasma. It's just a ball of hot plasma trapped in the gravitational potential well of the black hole and galaxy. And so we're going to zoom in to less than 1 kiloparsec, and you see the emergence of these tiny filaments. These are the filaments that we saw in the optical image at the center of the Perseus cluster, and they're formed by cooling instability. So self-consistently, these filaments are formed in his calculation from the dynamics of the hot emitting plasma and the cooling instabilities that are present in this hot emitting plasma. And if you just keep going, you can watch the time evolution as these filaments are falling in to the center, and then we'll zoom in and look at the structure of the filaments on 100 times smaller scales. Now we've zoomed in by another factor of 100, and now you see how these filaments are beginning to intersect and collect towards the center of the galaxy. Evolve it in time, and you see the formation of a little accretion disk, a little rotating disk in the middle. These are same calculation, but just 2 different views. We zoom in by another factor of 100 until we finally see the hole in the middle of the disk. And inside that hole are ever more filaments that are falling in. Zoom in yet again. Now we're down to 0.3 parsecs. We're getting there. We're almost there. Now we're seeing the very inner region. The disk is now 100 to 1,000 times farther radii. We're now seeing the very inner edge of the disk, filaments falling in. We'll zoom in one more time. That evolves for a little bit of time as you see these filaments orbiting around the black hole. Now we're getting down to black hole scales. And with one more zoom in, it starts to look like these accretion disk simulations I was just showing you. There's the GRMHD calculation I was just showing you of the MRI generating these spiral waves and turbulence all the way down the horizon. The black hole in the middle is the event horizon of the black hole in the center of this galaxy. So we're finally able to go from literally, the outer scale, the largest scale, and keep zooming in and zooming in and zooming in and zooming in until finally we reach the smallest scales. We can now follow the flow of matter and energy released at the event horizon of the black hole. We can follow it all the way back out to kiloparsec scales and actually understand from first principles how AGN feedback actually affects the larger scales over cosmological times, which I think is very, very exciting. So with that, given the technical difficulties, I better quit. I've already taken too much of your time, so basically this is a very exciting time to be doing these kind of calculations, not only because of the observations like EHT and the new computers like the exascale, and we're able to, for the first time, model these high luminosity flows and really try to understand exactly how black hole accretion works and how black holes really affect their environment and how they affect cosmological evolution of galaxies and other things. It's very, very exciting times, in my view. Thank you very much.
Black hole is spinning. Yes, is it not like a pulsar? And it happens to spin across as we see it.
So,
Can you
excellent
re-
question.
Can you repeat the question?
Sure. If the black hole is producing a relativistic jet, is it not like a pulsar where the jet is being processing around? The answer is no, because the jet tends to be aligned with the spin of the black hole, and that's very, very stable. So unlike a pulsar where the radiation is coming off at some angle from the spin axis, and that's what's giving you this lighthouse effect, with the black hole, the jet tends to be just along the spin axis, and so you generally only see the jet coming out. Now, that's not strictly true. The jet relies on the magnetic field. It's an MHD process that produces the jet. And if the magnetic field, it has a pole, a direction, and if the direction of the magnetic field gets tilted to the spin axis, then the jet will tend to be not processing, but launched in a different direction from the spin axis. And so it won't be processing around, but it will be pointing in this somewhat different direction. Yes?
You mentioned that the matter falling to the black hole has to use angular momentum.
Yes.
So what happens to that angular momentum? It can't just go away.
It can't. Some fraction, of course, goes into the black hole, and that's what produces the black hole spin. But that's a very tiny fraction of the total. The total angular momentum of the spinning black hole in the middle is negligible compared to the amount of angular momentum associated with the plasma just falling in. That angular momentum gets lost in outflows. And so from these accretion disks, there's just as much matter flowing out, driven by magnetic and radiation forces, as there is flowing into the black hole. And all that wind, as it flows outwards, it's rotating, it's carrying angular momentum, and so there's a flux of angular momentum that's carried to infinity, basically. And so whatever plasma made it in, it had to lose all its angular momentum to its environment through MHD torques, mostly, and through mass flow through these winds. Yep.
Any prospect for quantum computers to go even beyond whatever it is?
Yes, exascale. This is a very interesting question. Of course, quantum computers are on the way, and they're very exciting as well. I don't understand exactly how they can be used for these kind of calculations, however. They're really very specialized devices that really work on only a subset of problems. The most famous being cryptography, right? And so, as we all know, quantum computers can factor numbers faster than any regular computer, and that will break all of our cryptography because all of our current cryptography is based on factoring numbers, which is relatively slow. And if it wasn't for the invention of an algorithm, a numerical algorithm for factoring numbers that works in quantum computers, then this wouldn't be interesting, because it just happens to be a very, very special algorithm that turns out to work very well in quantum computers that enables this to happen. Similarly, there's some other problems where there are algorithms that can map to quantum computers that will be very, very important. And perhaps I'm no expert, but I understand one important area is drug design, for example. You can calculate the structure of molecules directly with quantum computers. Sort of makes sense because that's quantum dynamics of the molecular scale, and that's what some quantum computers are going to be very, very good at. So we'll be able to design ab initio models of molecules directly. We can make whatever molecule we want on the computer and then be able to form it in the lab. But how do you solve PDEs, and how do you use the numerical algorithms that we use for fluid dynamics? Currently, there's no algorithms that I'm aware of that map to quantum computers. And so I think quantum computers would be the kind of thing that there's some fields it's going to be revolutionary for, and there's other things it's not really going to do much for. And we'll benefit from the things it works on, and we'll try to think about how to do other things better. Yes.
Does your model suggest that most every black hole eventually will obtain an accretion disk in the manner you're modeling, or does it depend on the distribution of mass in the galaxy in the first place?
We think that probably every single black hole will have gone through some kind of accretion event. In fact, there's a very interesting story about so-called little red dots discovered by JWST. These are very enigmatic, extremely high redshift sources that are the centers of newly forming galaxies, and they don't really look like any other kind of galaxy we know of. And they're currently one of the most attractive models for those are so-called super Eddington accretion flows, as we were just discussing here. Namely, there is a say 10 to the 4 solar mass or 10 to the 5 solar mass black hole at the center of these galaxies. These galaxies are only a few 100 million years old. They formed a few 100 million years after the Big Bang. So we are looking back 13.4 billion years to see these newly formed galaxies, and they contain relatively low mass black holes that are accreting at enormous rates, much, much higher than normal AGN in our local universe. And so they're probably growing very, very rapidly for a short period of time. This may be a very common phase of black hole growth in the early universe. This is literally a new discovery from JWST that's sort of revolutionizing the way we think about black hole growth in the early universe. And so it's quite plausible that for at least supermassive black holes, they all go through a period of very, very rapid growth or through growth through accretion of mass. Yep. Yep.
It's a non-relativistic question, but have these techniques been used to model the Earth's magnetic field?
Similar techniques, yes. It's quite a different parameter regime because it's incompressible fluid dynamics as opposed to the highly compressible dynamics of these plasmas. And also it's a very, very resistive and diffusive environment. So the magnetic field is only kind of weakly tied to the rock. It can diffuse fairly easily. But yes, very similar methods for MHD have been used to try to study dynamos, not just for the Earth, but an even more interesting one to most astronomers is the sun. We have this 22-year period. No one can explain why 22 years for something that's, 4.5 billion years old. And so there's a number of groups around the world that are using nearly identical techniques to what I described here to model the solar dynamo and see if we can figure out exactly what causes the sun's magnetic field to evolve in the way it does. It's a really interesting problem in fluid dynamics, basically, basic fluid dynamics.
We have a question online. How powerful can the relativistic outflows from black holes become? And since bipolar outflows from protostars can form Haro objects, can black hole jets form similar objects on a much larger scale?
It's very good questions.
Yeah.
I mean, these jets can be extremely powerful. I mean, 10 to the 46 ergs, I believe, in some of the most powerful cases. I'm not sure how to put that in context, but they can be, much, much more luminous than stars or collections of stars in the galaxy. So but most of the energy is coming out in relativistic electrons and in magnetic field. It's not in light per se, but in energy in other forms. Energy in the form of magnetic fields and energy in the form of relativistic particles. So that means they don't really form Haro objects like protostellar jets. Those jets are only a few 100 kilometers per second. They sweep up dense gas in the interstellar medium. They make these Haro objects. We do see the jets being variable. They change in time, and we have movies of the jet in M87 as these blobs of plasma come out from the center of the galaxy. And so they are variable like Haro objects, but they're variable in a different way, and the mechanism that generates the knots you see in relativistic jets different than the way you generate them in Haro and protostellar jets.
That M87 jet you showed, is that visible in modest telescopes? I don't remember ever photographing that. Do you know anything about that?
Surely somebody in this room was much better than me.
Do you think you can see it?
I mean, the image I showed you was just an optical telescope image, yes. So, most of the emission's coming out in the radio, but there is some very high energy electrons that generate optical photons, and that's that little filament that you see. That image was actually taken with HST, so and that probably helps a lot. Yes, yes.
C-star. There's a whole group, subgroup, what, increase in C-stars. Seriously? Right.
So the answer is yes?
C-star.
Okay.
That's the-
Okay.
I'm sort of trying.
We gotta go all look at our
images.
You know, a lot of stuff.
Imagine a telescope that's the size of the Earth.
Yes, 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 yes.
Is there anything like Bolos putting this stuff in outer space? Supercomputer would seem reasonable.
Putting the computers in space hasn't really been considered because they're very delicate, would not survive in space environment. They also, I mean, the dirty secret is that they crash all the time. Every single day they have to be rebooted. They have a huge staff that are there just to care for them, to keep them running. They're very, very fragile.
Like if they could look at satellites and put them in orbit around the sun, would you get a Mondes telescope?
So yes, and so the first part of the question, absolutely. So what's the first thing you think of if you built a telescope the size of the Earth? What are you going to do next? Of course, you're going to go to space. And so there is a proposal to NASA to launch a radio telescope into Earth orbit. It would form another link in EHT. It would be located several Earth radii away from the surface, and it would just be collecting radio data and be another link. And then you would have baselines that are several times the diameter of the Earth, and you'd be able to increase the resolution by a factor of a few again. The challenge is that these are so-called interferometers, right? You collect the data and you ship it to one central location, so-called correlate the data. And the data means you have to store the entire time and frequency amplitude information from the telescope, which is an enormous data stream. And so currently it far exceeds what the internet can handle. So the only way this works is they literally fly banks of hard drives from each telescope to Boston, where they then get plugged into a big computer and then they're all analyzed. What do you do in space? They're literally talking about, dropping, canisters of hard drives and then collecting those, because currently the deep space network is completely overwhelmed. It would never be able to have the bandwidth. So either NASA would have to build a brand new radio communication link which it really needs because we have so many satellites now, but that's a lot of money, or they have to do something else novel. And so that's really the big challenge for doing radio interferometry for space.
I guess until recently, I thought a black hole was like, there was a black hole object, and then with that horizon news. But if you imagine like Neptune, like the core would be like a black hole object, that big atmosphere would be the region for that fly. But I guess it's not. It's just an event horizon with singularity or something.
Yeah, it's more like, it's a hole. It's a membrane where stuff can fall in and stuff can get dragged in, but can't come out. There's no object inside. There's no object inside. And sorry? It has mass. It has, spin. It has charge. The only three things that a black hole can have. And
like a photon has dimensions, right? It has a size.
Well, I mean, it's a massless particle, so it's just really energy. It's just, it's just a oscillation of magnetic electric fields.
See illustration.
No, it's not a particle. It's really a conceptual idea of, quantized piece of energy.
I just thought it was weird that they seem like opposite. One has mass but no dimension, the other one has dimensions but no mass.
Yeah, that's the big difference is black holes have mass, photons do not have mass, and that makes them weird. Yes. Yep.
When you were referring to power usage by the massive computers you
Yes.
guys use, what are we talking about? Kilowatts per
Uh,
hour or megawatts?
Megawatts. I think the machine in Oak Ridge is 30 megawatts. So it's the entire usage of Princeton for that one computer. So it runs a small town of like 30,000 houses. And so they're located where they're entering. It's at Oak Ridge because in World War II, that's where they built all the electrical uranium separation units. There's these huge dams, the Tennessee Valley Authority. There's a lot of free hydroelectricity there. So that's why that computer is in Tennessee, because it's close to clean hydroelectricity that can be used to power that computer. And yeah, finding power sources is the main limitation for data centers right now, and that's biggest factor. Yep. Well, this is the great thing that up to now has been true. We don't pay anything. The DOE owns these computers. They make some fraction of the time available for general science. And so you write a proposal, So we and thousands of other scientists around the country propose to do certain calculations, and then a panel of scientists meets and reads through all the proposals and selects the ones they think would be the most interesting and impactful, and then those proposals get allocated a certain amount of time, whatever time's available. You know, they're making huge amounts of time available for computational science, not only in astrophysics, but, you know, everything from material science to, you know, physics to chemistry, biology, all the sciences are. And no, the only thing the DOE uses these computers for is for their own computational science problems, right? The DOE is responsible for stockpile stewardship and understanding nuclear weapons, and so they use those computers to also model weapons. And so some fraction of the time is dedicated to that, although in these computers it's very little, and most of the time goes towards open science. That's been the model to date, you know, this wonderful support of science by the federal government. You know, as of now, that's ending, and maybe these computers won't exist next year. I don't know. I don't know.
You mentioned DOE, what's the abbreviation?
Sorry, Department of Energy, as opposed to Department of Education, which no longer exists, but Department of Energy still exists. Right. There's always this leapfrog. Currently, the US machines are #1 in the world, but as of like 2 or 3 years ago, there was a machine in China which was faster. Now, in fact, you know, they measure the performance by running a certain test benchmark on it. And some manufacturers just build a computer that only runs that, and they can't really do anything else. And that way they get to be #1 on the list, and that was what was happening. So I happen to know from my colleagues in China that hardly anybody can ever use the machines they have because they just don't really work very well. But even though they were listed as #1 on the so-called top 500 list. These computers are actually built out of general purpose, you know, NVIDIA GPUs or Intel GPUs, the same ones that you could buy, or you used to be able to buy, that are so hard to get nowadays. So they're just commodity hardware that come off the shelf. You know, what's unique about them is the way they're interconnected. These machines have 100,000 GPUs in them. That's a lot, and the way they're interconnected is very complicated, and that's unique to the machine, a very special hardware that handles the networking between the GPUs.
Do they have a finite lifespan, or they'd be outmoded in that in their life?
They generally have a 3 to 5 year lifespan before they start wearing down. They literally begin to break down a lot. But in that time period, generally the vendor comes up with 2 or 3 new designs that are much better. And so you want to get a new machine anyways, because the old machine is just too slow. I think the really interesting and important development is all these low power processors that are driven by our insatiable demand for mobile devices. And so the biggest development in computer architecture right now is building low power processors. So those are what's needed for building big computers. And so I feel like at some point the processors in your iPhone will be what's going inside these big computers, because they will be more power efficient than GPUs at some point. And so I think there's an enormous development possible. And I don't think this is the end of computing development. I mean, already the vendors said they will have machines 1,000 times faster in the next 10 years based on their current design. So that's great. I mean, it means that students today are going to be doing even more amazing things 10 years from now that we can't really imagine. Things that we think are hard in these machines will just be easy. No.
One last question maybe, and then we'll call intermission. Okay, please.
During the black hole merger with 2 black holes with opposite rotations, was the matter you achieved it be pulled in because they're
So let me understand correctly. You're thinking of 2 black holes which have opposite spins, and then what happens to that? That's a super interesting question, because we think there are such binary black holes, but you can't have 2 black holes that are just sort of stationary, because they would just pull each other in together. So they have to be orbiting around each other like the Earth orbits the sun. So then that's what you would call a binary black hole. And then the matter that's falling in it can, first of all, it's rotating around both of them, so-called circumbinary disk, where instead of a single black hole at the middle with this plasma orbiting around it, now you have two little black holes in the middle with this bigger disk around that. And then as it falls in, it has to decide which black hole it's going to fall into. Is it going to go on the right one or the left one? And then it forms a little disk around that and then falls in. So as you can imagine, the dynamics of that's even more complicated, because on the scale of the separation of these two black holes, you have these interacting streams as they go from one black hole to the other. On the larger scale, you have this, time-dependent dipole potential from the orbiting black hole. And so I haven't shown you, but there's a lot of interest and a lot of calculations on these so-called circumbinary disk evolutions. And we think it's important because we think some of the black holes at the center of galaxies, like I've shown you today, are actually binary black holes. And LISA, this new gravitational wave detector in space that's launched in about 5 years, will be able to detect gravitational waves from these binary black holes. So we want to be able to predict what they're going to look like and what we should expect from this new LISA mission. So it's a very, very timely and very, very active area of research right now, actually.
I'd like to introduce our Unjournal Club presenter tonight. Maya Chu is one of our student members. She's also one of the starting members of the Unistellar project team, so we may have more to hear from her later this year. But nonetheless, Maya's volunteered to talk about a topic. I think she's put a little thought into this, the RR Lyra variable stars. So we'll learn a little bit about stellar astronomy now. Take it away.
Okay, so I'll be talking about variable stars, and I'll just begin. So first of all, variable stars are typically split into two categories. You have the extrinsic variables and then the intrinsic variables. So extrinsic variable stars are the ones that change in brightness due to external factors. So the first example here is rotating stars. This is when the star has star spots on its surface, and this is typically regions that are much cooler in temperature. And so when the star rotates so that these regions are facing the Earth, and when we observe the star, it would appear that the brightness would be dimming. And then the second type I have here is eclipsing binaries. This is when you have two stars rotating around each other and they're like pretty close and gravitationally bound. And then when you have one star rotating to be in front of the other, when it's like facing Earth, then you have that star blocking the brightness of the other star. And then you would observe these dips in the brightness. The second type is intrinsic variables. So this is when the star brightness is changing due to internal processes inside the star. The most common kind would be pulsating stars like Cepheids and R Lyrae. These typically have pretty short periods of like 0.5 a day to maybe 3 or 5 days. And then you also have like longer period variables, which whose brightness change every a few months or even like a few years. And then lastly, of course, you have the novae, the recurrent novae, and then when they explode, you see them getting much brighter in the sky. Like I think one example recently would be T Corona Borealis. So I've talked about the stars, and then here are some that you can actually like see in the night sky in the summer. So the first two are like really bright. They're observable by the naked eye. You have Delta Sep and Beta Lyrae. So for example, here Delta Sep, the numbers are the magnitude. So it changes from when it's brightest, it's at 3.5 and 4.4 at the dimmest. So this magnitude change of 1 is really like observable even if you just like go outside and look at it with your eyes. Yeah. Then you also have like these three other stars, which are like slightly dimmer, but you can see them with your binoculars. And then there is one particular one, W Ursa Majoris. It has an extremely short period of just 1/3 of a day, which means that over the night you can sort of like see its brightness change. And then so going into RR Lyrae specifically, these are like a certain stars that when they leave the main sequence and they start to die, they pulsate in size and brightness. So there's like the force that's sort of compressing the star due to gravity, and then there's the force causing the star to expand because of the radiation. And then when you have these forces sort of balanced out, the star goes onto this instability strip where it starts to pulsate. There's also like this physics sort of mechanism involved called the Kappa mechanism. But anyways, what you get is that when the star is expanded, it's like cooler in temperature and you can see it dimmer. And then when it's like compressed and smaller, it would be hotter, so you can see it would also be brighter. And then the reason that we care about our Lyrae stars is that it can indicate the distance because they are used as standard candles. So how standard candles work is that when you observe these stars, so you can find the period and like period of like how often the brightness is changing, right? And then basically there are these equations where once you know the period, you can also find the star's luminosity and brightness. The luminosity is like the energy the star is like radiating from its surface. And then once you know all these things, you can actually calculate the distance of the star, how far it is from us. And then you have that equation on the slide there. And then the graph on the right sort of just shows the relation. So once you have the period, you can sort of find the absolute magnitude. You can see this is actually from like a paper. You can see the sort of like linear relationship. So yeah. And then, so this means that you can find the distance using our Lyraes, and that can help us sort of map out the universe. And this here is the Blaschko effect. It's like a specific thing that certain R Lyraes exhibit. I believe around 20 to 30% of the stars exhibit this effect. It's really cool is essentially you have the blue wave up there, which is the star pulsating in brightness and size. But then you have the second wave, red wave, it's like the second overtone. And when you overlap the two, you get this purple wave below, which sort of shows that not only is the star changing in brightness, its amplitude and period is also changing. Like, for example, here you might have the star magnitude changing from like 5 to 5.2. And then here, when the amplitude is larger, the star's magnitude might be like changing from like 4.95 to 5.25. So you can observe the amplitude changing and the period changing for some of these stars. And there is a bit of mystery involved in this effect, actually. There's like a lot of explanations, but the exact cause of this is unknown, even though we have observed this in like many, many R Lyraes. And so I did a project on these stars, and specifically I chose this cluster NGC 301. It's a pretty bright globular cluster, so it's pretty old and there's a lot of stars in it, which is why it's nice for like a variable star study. You can theoretically observe it with a binocular because the magnitude is like 6.7, but unfortunately it's in the southern hemisphere. So, and on the right is like a color image, like when you take images in 3 filters and then you put it together. So that's like what the cluster would actually look like. And you can see in the center there's like a lot of stars. It's really dense. And then here's the same image with all the R Lyrae stars marked out. So there's really a lot of them. In fact, there's like a total of 160 variable stars in this particular cluster. For the project, I picked 4 that were like sort of on the edge of the cluster because those stars are more easily resolved. And then there was just a lot of code involved. The images were taken from this observatory called LCO, Las Cumbres Observatory. They have like telescopes around the world. I think there's ones in like Chile, Australia, and everything. So it's really nice because it allows you to observe the star for like extended periods of time. It might be like setting in one place and then another telescope from a different location can keep tracking the clusters. So you can get a lot of data from these. And then there are a lot of code. There's the plate solving, the photometry. You need like these comparison stars nearby to find its brightness. And then once you have like the star's brightness, you code algorithms to find the optimal period. So this is an example of one of the stars. So on the top where it says P equals 0.5263 D, that's like the period. So on the left would be its optimal period of 0.53 days. And then on the left here, you see if you fit it to 0.57 days, the data is much more messy and you don't see this clean light curve. And that's how we know that this would be the correct period. And the changing color there is also indicative of the temperature. So you can see the temperature changing with the brightness. And then this last slide is like the results of the 4 stars. You can see, so it gets brighter much faster than it dims, but you can sort of see the process when you get all the data points on the graph. And then, I believe the periods are not shown in this particular plot, but basically when we found the periods and compared it to the catalogs online, we found that it was like quite different from past years. Like I believe for V6 there was maybe like maybe 10 or 20 minutes of difference, but then for V66 there were like a couple hours of difference. So you can sort of observe that the star's period is changing, which is how we know that it is exhibiting the Blasco effect that I was talking about. But yeah, that's our Lyrae stars, and I think they're really cool.